Okay, good morning. Good morning to the next lecture on electricity and magnetism. Yesterday, we looked at the concept of the capacitance. And if you recall, what we said is that we are taking two conductors and we place them somewhere in space and then we charging them up. So this charging, that means we are putting a positive charge on the one conductor and a negative on the other one. That basically can be done if you think you're taking one charge, one electron from conductor L1 and move it over to the conductor 2. You kind of, well, take it and move it over through space and place it on the conductor 2. And you do that one by one. So you can do that in the end by applying some voltage to the two conductors. And we will see also that there's some energy, some work that needs to be done in order to perform this charging process. This comes up later. But right now, we are assuming that we reach this final equilibrium state where you have this charge distributed. And then we see that we can actually define something like a capacitance, which is charge per voltage, Q over U, and that's the capacitance. And this is a measure basically on how much charge you will hold on these conductors based on a given voltage that you apply to them. And this capacitance is actually a purely, it doesn't depend on the charge, it doesn't depend on the voltage, but this is a property that depends on the geometry and on the material parameters. I see it's a geometry, and on the material parameters. And now we wanted to quantify what is this capacitance for the specific case where we have a parallel plate capacitor. That means we have two plates which are large in extent, large in plate area compared to the separation of these two plates. And these plates are in between filled with some material, or it could be also vacuum, but we can assume in general that there is some dielectric in between that can have some permittivity. So we denote that permittivity here as E naught times ER. ER is the relative permittivity. And then we want to see what is the capacitance. So we look at the voltage. The voltage is obtained by integrating the electric field over this gap. And we know that with this type of configuration, we actually have a homogeneous E field inside that gap. There are some stray fields possibly towards the end of the plates, but we will neglect them. And then means we can derive the capacitance as follows. We take the voltage that is obtained by integrating over the E field, and the E field is conveniently now homogeneous. It is constant, and it is all oriented here, if you look with respect to this graph, in Z direction. So it comes down that the voltage you want to is actually just the Ez times the plate separation D. And on the charge side, we know that the charge is given by the by the electric displacement field and times the area of the plate. And there I would like go quickly make a bit short comment, because we said earlier we have two kinds of fields, which is one, the electric field, and it is the displacement field. And these are just related to each other with this permittivity. So there's, however, if you look what the permittivity is in terms of units, or even, it has this 8.85 roughly. It is roughly this 8.85 times 10 to the minus 12. This is a 12 here. 12 ampere second per voltmeter. Now, if you look at the electric field, you have a unit which is volt per meter. If you look at the electric displacement, you have the permittivity times the electric field, and in terms of units, you get these ampere second per voltmeter times voltmeter, and that is ampere second per square meter. So this displacement field has also a second name, which is the electric flux density. And when you look at that, when you look at how we use these terms, there's quite a difference, because if you have an electric field and you integrate over an electric field quantity, then that would be, for example, because you want to determine a voltage. And the voltage would be then the electric field over a distance. You would integrate this over a path. If you do any integration on this flux density, on the displacement field, then you do an integration like you saw in Gauss's law, that you actually do an integration over a surface and you obtain then some charge. So these two fields, they're just connected through these permittivity. But if you look what they represent, this here is a quantity which is charge per square meter. It is a flux, something that you look at that goes through an area. And the electric field, this is more something where it is basically a force field. It is normalized to the charge. If you take an integration on the electric field, then you do that over a line. So conceptually, there's some difference. And when we were looking at, for example, yesterday we introduced, in addition, this is Gauss's law, right? And we introduced that we can also actually make use of using here volume integral. So this is, in that specific case of Gauss's law, we will integrate over an enclosing surface of a volume, also a surface. But then on the right-hand side, we can equate that to a volume integral over a space charge density. But we can also, instead of with a space charge density, we can also work with a surface charge density. So space charge is something where you have ampere second per cubic meter, but we can also work with the surface charge density, which we denote as sigma, where you have ampere seconds per square meter. And of course, the charge always is something that has, on the microscopic level, a certain volume extension. It's something three-dimensional. But we nevertheless, often it becomes advantageous to work with a surface charge, because essentially these charges are then all found at one very thin layer, and it is useful to work with the concept of having charge per area. So in that case, you take here an area integral over sigma. Now, we had the aspect, what happens if you have a surface charge on a conductor here, and you go about and integrate here the d field on this volume. Now you have a d field that is oriented in this direction. Also, your surface element here has this orientation here. So this is basically your normal orientation. Now think of making this volume smaller and smaller. Then, because it is a conductor actually, you know, if you take this integral over this surface, over this enclosed surface, then you will see if you make this slimmer and slimmer here, you have no contribution here along these lines anyway. They would be also perpendicular here, or they would be aligned with the electric flux density. Inside here, you also have no contribution because you're in a conductor. And we said in a conductor, you never have an electric field. So in the end, in this situation, you can actually just take the d field, which is ampere second per square meter, and multiply it with the area that you're looking at, and then you get your surface charge. So this is what you see here, that we say the surface charge is just the product of the flux density, electric flux density, which is same as the displacement field, times here the normal contribution. You see, this is already ampere second per square meter. You have to evaluate that in the end over some area, and you multiply it by the area, then you end up with the surface charge. So for that example here, we obtain the charge by taking the flux density, the electric flux density, respectively the electric displacement field at that interface, and multiply it, and it is constant over the entire interface, and multiply it by the size of the interface. That is just our surface density. And from that, we have both obtained in this model. We have two parallel plates. We have said we have a charge given that we have on either plate, and they are of this in magnitude, they're always the same. They are just of opposing sign. And so we can tell what the voltage is, we can tell what the charge is, and there's a relation also because of the voltage is related to the E field. The E field is related to the flux density. And so we can give expression for the capacitor, for the capacitance. And you see this is all purely in material and geometrical properties. So what enters here is the size of the area of the plate, so the area of these plates. So each plate has an area of A. The plate separation is given with D, and the epsilon, the permittivity, that also enters into the formula for this parallel plate capacitor. And you see also that if you want to enhance the capacitance, and enhancing the capacitance means here that at a given charge, at a given voltage applied, you can store more charge if you have a higher capacitance. You use the same voltage, for example, but you have a larger capacitance. Now that means because it is larger, the capacitance, at the same voltage, you get more charge stored on it. So the capacitance is purely dependent on geometrical and parameter properties. And you can, in this example, you see you can enhance or make the capacitance larger if you take here an epsilon r, or relative epsilon r, which is larger. Questions? So this is important, this formula. These two things here, they actually entered into this formula. And this here is only a function of geometry and material. And also this formula is, while you can have find a capacitance for all kinds of geometries, this particular formula that is given here is only valid for this parallel plate capacitor. So this is a capacitance of, so it must be parallel. So if you have some capacitor that looks something like one plate like this and the other plate like this, you can do that too, but this is not valid for this. So yeah, if you have such a capacitor, you cannot use this formula. Let's look at some different arrangements of capacitors. Where did it go? Okay, yeah, I got it. So we can have different configurations or different aggregations or arrangements of capacitors. And the first one is what happens if we have a set of n capacitors which are all put in parallel. So this is what you see here. You see a circuit representation of a number of capacitors. This is capacitor 1, 2, and so on till you have here capacitor n. So we have n capacitors in parallel. These capacitors are named C sub I, and we have the I running here from 1 to n. So we have a voltage here at the port, and we have our C1 here, C2, C3, and so on till we are at Cn. And we have over the capacitor here a voltage U1, U2, U3, and Un. So we know that the capacitance is defined as charge over voltage. And also for the parallel plate capacitor, we know, I assume for this formula that it is a parallel plate capacitor, but of course this does not have to be like that. So this switching these capacitors in parallel, that works for arbitrary kinds of capacitors. Only this formula that I've given here, that would be for a parallel plate capacitor only. So now our question is, how can we find an equivalent circuit representation which describes this configuration by a single capacitance? So we would like to have now an equivalent circuit of what we have here above. But this equivalent circuit should not contain a number of parallel capacitors. It actually should only contain a single capacitance. And that I denote with Cp, because for the scenario where we have these capacitors in parallel, I call it Cp. But this single capacitor should have the property of all these n capacitors in parallel. So the Cp is now the capacitance of the whole circuit. So we have these I individual capacitors in the original problem. And for those, we know what the capacitance is. That we know the general relation. The capacitance is Q over U. So for the individual one, for C sub I, we know that C sub I is Q sub I, which is the charge on the ith capacitor and the voltage on the ith capacitor. Now, if you look at that equivalent circuit above, then we see immediately that actually the voltages are all the same because they are in parallel. We have U1 equal to U2 equal to U3, and basically all of them equal are the same. So is equal to basically U sub I and so on. And this is equal to U. However, what is the charge on the individual capacitors? What is this? Well, we have different capacitors possibly, but we have the same voltage. And since we can have different capacitors, because we have just said we have a number of parallel plate capacitors, but no mentioning that they were, for example, the same. So these all have a different capacitance, but they share the same voltage. So we have different C sub I. However, we have the same voltage for all of them. U sub I is U. So since the capacitances are different, we can also say that the charges are different. Q sub I will be not the same as Q sub 2, will be not the same as Q sub 3 in general. However, the Q sub I will be always related to the voltage and the capacitance. It will be C sub I times U. So now we have these two aspects. On the one hand, we want to have here a new equivalent circuit which substitutes the number of n parallel capacitors with a single capacitor called C sub P. That is our goal. So this is what we like to have. We like to have C sub P so that C sub P gives us the total charge, which should be the same as in the first example, over the voltage U. And this total charge we obtain then by adding up the individual charges. So we have to add up, we have to sum up for I is 1 to n, all the individual contributions of charges on the individual capacitors. And this we can do now by using this formula also, is obtained by here taking a summation for I is equal 1 to n C sub I times U. So the total charge is what we need here. Q total is then in the new equivalent circuit Cp times U. And this Q total is also, as we see in the line above, the summation of I running from 1 to n over C sub 1 times U. See that from here. So now you just compare these two sides, the left hand and the right hand side, and you can conclude what the new total capacitance should be. The total capacitance of the above circuit is, you see that here from what I marked with yellow, the Cp is equivalent of taking the sum of the individual capacitances. So if you have a circuit where you put in several capacitances in parallel, the equivalent capacitance, which represents all these capacitances switched in parallel, is obtained by summing up the individual capacitances. This is equation 1.48. And now we have an equivalent circuit representation. It's down a bit. So you have your ports here, you have the voltage applied, and you have your total charge here on that capacitor. And this capacitor is now called Cp, and it's the sum of the individual capacitors that we had in the original problem. So you have a new equivalent circuit. So this is the one scenario. A different scenario could be actually that you have a parallel, sorry, not the parallel we just had now, that you have a serial switching. You switch all these, you have a set of capacitors of arbitrary kind and you put them in series. So again, n capacitors in serial configuration, the capacitors are again named C sub I, with I running from 1 to n. And you see that equivalent circuit here now. You have again a voltage applied at this port. You have here capacitor 1, capacitor 2, capacitor 3, and so on till you have here capacitor n. And you have a voltage U sub I, U sub 2, U sub 3 over it, and so on, U sub n. Now, you would like to have a new equivalent circuit where you do just what we had done in the previous example, where you replace all of these capacitances with a single capacitance, which gives us an equivalent behavior, which means its overall capacitance is the same as that of all these capacitances switched in series. You have again here your Q total on the capacitor space here. So now we see the scenario is a bit different because we have voltages at the capacitors which are obviously different. In the previous example, they were all the same. So our U actually is splitting up, the total U here is splitting up into these individual components, U sub 1, U sub n. So U splits up, or let's say it splits up according to the capacitance values of C sub 1. So, but in general, we have that U1 is not equal U2, it's not equal U3, and so on, and is not equal UN, and this all is not equal to U. How about the charges? Well, we have at the first capacitor on the left-hand plate here charge of plus Q1, and on the right one we have a charge of minus Q1. Same here for the second, we have plus Q2 and minus Q2. Now, how do they relate to each other, these charges here? Well, the Q1 has to be equal to the Q2, and the minus is of course always opposite in magnitude, but opposite in sign, but same in magnitude. So why is it to be like that? Because you actually everywhere here you can separate these charges, but you cannot, yeah, all that you can do is a separation of the charges, but you have a conservation of the charges. And in that sense, you have the situation that the Q1 is equal to the Q2 is equal to the Q3. So they are all of the same magnitude. If that was not the case, if Q1 was not equal to Q2, then you would have a charge flowing from the one capacitor to the other until you have them equal. Eventually, you get into a stationary equilibrium, and then you will have Q1 equal to Q2 equal to Q3 is equal to Qn. Now our goal is to derive a formula for that equivalent circuit, and we denoted it here. This equivalent circuit, the capacitance is C sub S. That S signifies here that serial configuration. So CS should be a single capacitance which has equivalent property to the serial configuration of this multitude of n capacitors. Our goal is to derive a formula for CS, C sub S, and that, of course, is given by the total charge over U. This is what we're looking for. What is the total charge? Well, we just saw that charge is the same on every capacitor. So the Q total is actually Q1, is actually Q2, and so on is Qn, and we can just call it Q. How about our voltage, U? Well, that is actually the sum. Remember Kirchhoff's voltage law, the voltage from here to here and the voltage from here to here, they are the same. So we have U is the sum of all the individual voltage contributions of over the n capacitors. So our U total is the sum of the Ui. And now, as usual, we have the standard formulation that the capacitance on the individual capacitor are Q sub I over U sub I. So you insert that here. U sub I is basically then the summation of 1 over C sub I times Q sub I. But the Q is the same always for all of the capacitors in this serial configuration. So you can pull it out, and this is equivalent to Q sub I to Q. So you get here. So we have our formula here for the equivalent capacitance. It is obtained from Q total, which is this one, over U, which is this one here. And in our equivalent circuit, then we have U is Q total over the C in series configuration, and the Q total is Q. And so in this here, you take this here, so you obtain this part here, but U we also have seen is equivalent to this one here. So what is the equivalent capacitance value? There you compare basically these two here, and you obtain 1 over Cs is equal to the summation of 1 over C sub I. This is our equation 1.49. And this is a formula how you get an equivalent capacitance when you have a serial connection of capacitors. Are you familiar with that already? No space here. No. Small example, you have a series connection of 1 and 2 capacitors. The capacitor 1, C1, it has a capacitance C, and C2 has a capacitance 2C. So then you want to get your equivalent capacitance, and you take this formula. So 1 over Cs is equal to 1 over C1 plus 1 over C2, and you obtain that by taking, basically here, C, you bring them on the same denominator, which would be C1 times C2, and that up there in the numerator you would have C2 plus C1. And now you insert the specific values. C2 is 2C, C1 is C, and here you have 2C times C. You have 3C over 2C squared gives you 3 over 2C. So as a consequence, your new serial capacitance, which represents, your new equivalent capacitance, which is equivalent to the series capacitance of these two capacitors C1 and C2, is Cs equal to 2 times C over 3. And what is the unit for the capacitance? We have here, this is 1F, which stands for 1 farad. And you see the capacitance is charge per voltage. So you have ampere seconds per volt that equals to farad. So now let's look at an example how we can connect these to the physical build of some actual capacitors. So what happens if we have dielectric layers in parallel? And for that purpose, think of a parallel plate capacitor, which is filled with two different layers of dielectric material. and they are arranged in such a fashion that they are side by side. So basically, you see here a top and a bottom plate, and in the one region, we have one material that shall be here the left-hand side, and then on the right-hand side, we shall have a different material, different dielectric. So this is our epsilon 2, and this is our epsilon 1. How does this affect the overall capacitance of this parallel plate capacitor now that it is filled with two different materials side by side? So in terms of the geometry, it of course had a certain depth, but in terms of the width, this part is here filled with A1, with epsilon 1, and the area is given with A1, and the second region is filled with the material with a permittivity epsilon 2, and the area that it takes up is the area A2. Now we put a voltage between these two plates, the two electrodes, and we denote here we can basically separate this plate into two regions. The one region with the area A1 filled with the material epsilon 1 is the region 1, and the other one is here the region 2. The separation of these two plates is D. We are having a coordinate system where this here goes in Z direction, and these two are our electrodes. So inside we have an electric field, and we also have a displacement field that is here E field respectively. It's also our flux density that is oriented such that this is perpendicular. So let's collect a bit these parameters. So we have the region 1. In that region 1, we have a permittivity epsilon 1. We have an area 1. Then we have a region 2. There we have the permittivity epsilon 2 and the area A2. How about the electric field? Well, that would be E1 in the region 1 and E2 in the region 2. The D field would be D1 in the region 1 and D2 in the region 2. And then we also have a surface charge density and a surface charge. And the surface charge here, that be sigma 1, and we have a sigma 2 here. And that would be Q1 by A1, and that would be Q2 divided by A2. Now we can relate that to the example that we have just given before with these. We had two examples, one with the parallel plate capacitor set up and one with a parallel capacitor setup where they set up not necessarily parallel plate capacitors, but in general you have capacitors arranged in a parallel setup, or the other one was in a serial setup. And you see that this is coinciding with the setup where we have parallel switching of capacitors. Basically, this is our one node, this is the other node, potential node, and you can put in here an equivalent circuit, and you have here a C1 and a C2, and you have a Q1 and a U and a Q2 and a U. So you have the same U, the same voltage on either one because they are in a parallel configuration, and you can make use now of this equivalent circuit where you put in parallel two capacitances. And now let's look how that affects our total charge and in this arrangement. So the task is calculate total charge and voltage, and here are the total capacitance of this arrangement. The total capacitance of the arrangement, that will be then again C is Q divided by U, charge per voltage. The voltage is obtained by integrating over the electric field, over the gap of these in between these two plates. So basically to integrate from 0 to D over the electric field, because it is a parallel plate capacitor, we have the fortunate situation again that this electric field is oriented in Z direction only. And the integration path, we also choose to take it in Z direction. So that makes the are both aligned here. So this just becomes 1. And we have the comfortable situation that our voltage is just Ez times the plate separation D. So we have the same voltage for region 1 and 2, and we have the same distance for the plate separation, because we just have filled this parallel plate capacitor with two different materials on the right and left hand side. So in this particular scenario, we have same voltage. Why do we have the same voltage? Because we have applied, we have the same potential on the either electrode. We have the same distance. So from that follows that the EC is equal to E1 is equal to E2, and the EC is actually given by U over D the other way around. So that is the magnitude of the electric field. So same E field in 1 and 2. However, while we have the same E field, we have different material parameters, and since the epsilon 1 is not equal to epsilon 2, it follows that also D1 here is not equal to D2. Rather, D1, the electric flux density, is obtained, and I can, because this is so nice linearly arranged, I drop here now this vectorial aspect for the moment, a bit casually. The permittivity E1 times the electric field 1, that is our flux density in the first region. And for D2, we obtain that is epsilon 2 times E2, but actually we see that we can write that just here as epsilon 1 times E. So the E field is the same for both. So then we get epsilon 1 times U over D. And here you have also epsilon 2 times E. Then you have epsilon 2 times U over D. What is the charge on the plates? Let's calculate that as well. Now, you know the charge. We have here a surface charge, and the surface charge is basically equivalent to the flux density, because we have here the scenario that we discussed earlier, that is this Q over A. Recall that was what we spoke about, that you have a small surface element here on the conductor surface. This is a flux density, and the flux density at the conductor is equivalent to the charge per surface. Q is sigma times A. The charge on the plate is then sigma 1 times A1 plus sigma 2 times A2. And sigma is directly related to or is given by the flux density. The flux density we have just stated above. So that would be epsilon 1 times U over D, that is our sigma 1, plus epsilon 2 over U over D, that would be sigma 2 then. And this times A1 and this times A2. So this is our total charge. The U and the D is constant for both regions. We can pull it out. Then you get U over D times epsilon 1 times A1 plus epsilon 2 times A2. And hence we have here the charge, we have here the, sorry, we have here the charge, we have here the voltage applied. And then we know that the capacitance is charge over voltage, means just bring that down over to the other side. Then what remains is here, or let's take the whole expression here. For the charge is u over d, epsilon 1 a1 plus epsilon 2 times a2, and we divide that by u. We take out the u here again, and then we are at, you basically see, we can split this up again in a C1 and a C2, and that gives a justification. This is exactly the formula what we have for a parallel plate capacitor. This here essentially becomes our C2, and this here our C1. In this particular case, we have the situation that the surface, that at the surface of the electrodes, the charges split according, I mean, the densities are splitting according to the capacitance. So you have in the one region, you have a surface charge density sigma 1, while in the other one you have a surface charge density sigma 2, and they are different from each other. Yeah, the charge splits according to capacitance. So we have in the region 1, sigma 1 equal to d1 equal to q1 over a1. And in the region 2, you have sigma 2, which is equal to d2, is equal to q2 over a2. You have questions? Break? Okay, let's have a short break. Then we do the scenario with where we have the series setup, and then yeah, then we look at the energy. Quick break, 5-10 minutes. Let's make it.
Be tested or what's the scope? Because if you're still on chapter 1 now,
Yeah, I mean, chapter 2, you will see that it is about current, current density, currents. I think we will don't have to do go there much in depth, but have those relation between charges and currents. I think that should be feasible. But then,
oh, you also cannot say a lot. I know. Okay, thank you, Bob. Thank you.
okay, then let's proceed. Okay, let's proceed. And now we had a second example. First, we had the two equivalent circuit examples, one with parallel circuits, one with series circuits. We have seen now how we can make use of this equivalent circuit concept with two parallel capacitors for the parallel plate capacitors, where we have two media inserted side by side. And now we repeat the whole thing in a slightly different variation, and we use a parallel plate capacitor, but this time the scenario is slightly different. You saw in the first case, you have here a material epsilon 1 side by side with a material with a permittivity epsilon 2. And now we do the similar concept where we have these two layers on top of each other. So you have a material epsilon 1 here on the top, and on the bottom you have a second material that is epsilon 2. You have an area of this capacitor plate, which is denoted by A. you apply a voltage between these two plates, which is U. You have then, we denote that here our region 1. This is our region 2. And the permittivity is epsilon 1 in the first, and in the second region epsilon 2. This time the area is the same for either of those. We have surface charge densities. We have here a surface charge at the bottom. We have here a surface charge at the top. We have also here kind of a normal vector that we can give, n1 and n2. The orientation is again here such that the plates are separated at a distance d in z direction. So this here is 0. Here the interface between the first and the second material is at d1. And the total thickness is d1 plus d2. So we have basically material 1 has a thickness of t1 and the material 2 a thickness of d2. So here our n1 that I just plotted in there and our n2, these are normal vectors. They are the same in magnitude. They just oriented in different directions. So this magnitude is 1. The capacitance formula mind is Q over U. C is Q over U. And the surface charge is sigma here, which gives you the total charge by taking sigma times A. And we have at the bottom also a surface charge sigma, and it gives you the total charge, which is minus Q, which is also obtained by sigma times A. The electric field in region 1 is E sub 1, E sub 2 in region 2, and the D field D1 and D2. So now what is the total charge, and what is the voltage, and what is the total capacitance of this arrangement? So we first calculate Q. So at the top, that would be Q over A, and at the bottom, it would be minus Q over A. And that corresponds basically to the absolute value of the electric flux density that is our surface charge. So in the first case, where we had the top, we have this equal to d1 times n1 is Q over A. In the second case, we have d2 at the bottom times n2, and there we have a negative charge, so it's minus Q over A. But then also you have to consider that we have n2 oriented in opposing direction to n1. So our n2 is minus n1. And if you insert that here, then you get basically, they're otherwise oriented just in opposed direction, but otherwise they're both oriented in z direction. Insert here for n2 n1 in this last line here, so that you get minus d2 times n1 here is minus qa by inserting this here. And of course you can flip here the sign on either side, then you will arrive at the d field is d1 is d2. So the d field here is constant in this setup. However, if the dielectric material, okay, we have two dielectric slabs here. So the d field, the electric flux density is constant over the entire filling of the capacitor. However, the E field is not. The E field changes due to the different epsilon. So we have in the first region E1 is the electric flux density divided by epsilon 1, while in the second region we have the same dielectric flux density, d is equal to d2 divided by epsilon 2. That is our E field 2. Take the voltage. You obtain that by integrating from the top to the bottom the electric field. Luckily, the E field is oriented only in z direction, so we can drop here our vectorial considerations so that we have an E1 and we integrate over dz from 0 to d1. And then we keep going on from d1, we integrate to d1 plus d2 over the electric field 2. So, we get the voltage here between the two plates by integrating over the electric field. So we start here at the top and integrate all the way down to the bottom over the electric field. And we split up this integration path into one section from 0 to d, and the second section from d1. So from 0 to d1, the first section, from d1 to d1 plus d2, the second section. We know that the electric flux or the displacement field is constant, not however the electric field. The electric field is constant within each region, but compared to the different region, it is different. In the first region, you have the electric field also purely oriented in zeta direction, given by the flux density divided through the first material parameter epsilon 1. And in the second region, it is given by the flux density divided by the second material parameter epsilon 2. The flux density or um, the displacement field we obtain directly here from the surface charge. Yeah, we have the surface charge that gives us the flux density. So this becomes very agreeable because this is just E1 times D1. The second contribution to the integral, the second path, gives us E2 times D2. This is actually equal to the voltage 1, U1, and this gives us our voltage U2. And the electric field, we said, is obtained from the flux density. So we can also write it like that here. Now, the flux density is constant. We can pull it out of the bracket. Then it is d1 over epsilon 1 plus d2 over epsilon 2. And the d we have seen up here, the flux density is determined by the charge and the area. So that is basically Q over A. Now we have our Q here, Q, and then we also have our U. So our capacitance, that is what we would like to calculate, is Q over U, Q over, and the U we just have here above, that is Q over A times D1 over epsilon 1 plus D2 over epsilon 2. You see that Q here canceled out. So we have remaining here A over D1 over epsilon 1 plus D2 over epsilon. And this is our capacitance. Just copy it down again. This is a formula for the capacitance where we have two material slabs in a series configuration. And to highlight here, the D field in this configuration is continuous here over the interface of the where we switch from material 1 to material 2 also. However, the E field is not. There's a jump in the E field at the interface when we transition from epsilon 1 to epsilon 2. So if you look at this example, you have here your top layer, you have here your bottom. On the top, you have a charge Q plus. On the bottom, you have a charge Q minus. In between, you have two materials. You have a voltage that accumulates from U1, from the starting position to D1, and then from D1 to D2, you have a second voltage. You have the overall voltage, U. You have a top surface charge and you have a bottom surface charge. And this is represented by an equivalent circuit of this type, where you have two capacitors put in series with each other. The one has a capacitance, because this is a parallel plate setup, of epsilon 1a over d1, and the other one of epsilon 2 times a over d2. And if you are looking at the formula that we had derived for series connection of capacitors, then we had said that the resulting total capacitance in the series connection, so this is C here, and 1 over C is given by taking 1 over C1 plus 1 over C2. So you basically get the inverse value of the capacitance of the total by adding up all the inverse values. This is C1 plus C2 over C1 times C2. And for that reason, if we flip around the numerator and denominator, that means C1 times C2 divided by C1 plus C2. Insert here these values for the individual capacitors. That is epsilon 1 times A1 over D1. We make use of this formula. We have taken, these are the individual capacitor values. We insert those here. Down there we have, now you can see that you can take out this A here that appears everywhere. You can reduce, sorry, no, I was a bit quick. Sorry. There and out there it comes as a product. Of course, we can only take one out, and we can take one out there. And what remains then here is 1A remains. So we divide that by epsilon 1 times epsilon 2 and multiply it by D1 and D2 in the numerator and denominator. And then we get D1 over epsilon 1 plus D2 over epsilon 2. So this is our formula that we obtain by connecting these two capacitors in series. And now if you compare it to the formulation that we have derived, you see that is a perfect match. So we see that this confirms that we can represent this parallel plate capacitor, which has two fillings which are on top of each other. So they're not next to each other, but on top of each other. We can split this into a series of multiple capacitors, and you see that equivalent circuit. If we use that, that gives us identical results here. So this is a valid, verifies that this is a valid equivalent circuit model for this parallel plate capacitor with two fillings stacked on top of another. You have questions? So this far we have assumed that we have a charged capacitor. Now we want to look a bit into this charging process, how we can figure out what is energy that is being stored in capacitor. And for that, we have to look in the charging process. And I want to depict this here for you. So we have an arbitrary configuration in terms of geometry and material. So we have here conductor 1, which I denote with L1. And then we have an arbitrary shaped second conductor, which I denote with L2. And I want to charge this capacitor. So we have said we have two conductors, so they form a capacitor, and this capacitance that we can assign to it, which is, by the way, then given as the capacitance is given with C is Q over U. So we want to see what energy is needed to charge the capacity, and we want to show also that this energy is then stored inside the electric field. So we consider a capacitor which consists of two conductors. This is this conductor L1 and L2. And we have to get a voltage between these two conductors. So, and that we achieve actually by you take a small charge here from that conductor L1, you take an electron and you grab it and you place it onto the conductor L2. So you take this delta Q, you take away from the um, conductor L1 and you place it into L2. So now the question is, how easy is this? Well, for the first one is actually quite easy because you can assume that uh, there's no charge on either of the capacitors or on either of these electrodes when you start. So the capacitor is formed by the um, arrangement of these two electrodes. But since there's no charge initially on either of these electrodes, there's also no electric field between these um, electrodes. So it's very easy to take a charge and move it over because you don't move it through an electric field. But as soon as you have started to bring your first charge over from, from the one conductor to the second conductor, you start to build up an electric field because you have now, yeah, you have one positively charged, the other one is negatively charged. So there's an electric field between these two conductors. So you take another charge from conductor L1, and now you have to move this charge through the electric field. And that requires some work. So you place it in the conductor L2, and then you take a further charge from conductor L1. But now, because you have already shifted one more charge, the electric field grows even stronger, and it takes you more work to overcome this electric field. So your task is now move this delta Q, which is larger than 0, from L1 to L2. You have, in consequence of yourself moving these charges, you have an E field which is building up. So the E field builds up, and during this charging process, you have to overcome an electric force. You have to overcome the electric force, and the electric force is given by the charge that you are moving and the electric field at whatever place you are with your charge currently. So in consequence, you need to perform a mechanical work, and this is performed. We have a mechanical work which is performed to charge the capacitor. So every time you move some charge, there's a change in the electric energy. The electric energy is then W electric. So there's a change, this is a delta W electric. And that is opposed to the to the change in energy that you perform mechanically. And this delta in the electric energy is obtained by integrating here from on a path from one conductor to the other, the charge times the electric field over the path. So charge times electric field, that's the force. You integrate the force over a path. That is your energy that is needed. The charge is not changing along that process. Every time you move another delta of charge, um, it will be this same type of delta of charge, but your electric field changes eventually. But at that instance where you just change a delta of the energy, in this moment the electric field is also constant in this single process. So you basically get here, this integral is just U1, 2. So the voltage between the two electrodes as a function of Q. So now the important aspect is here that this voltage, this is fine for a single, what we have written down is very straightforward for a single delta Q, but you see that that voltage 1 to 2, so the voltage between these two conductors actually changes as the charge on the plates is changing. So this U12 is a function of Q since the voltage changes during the charges process. So this delta means we are dealing with a very small amount. So this is a very small delta, yeah. And we slowly then transition to the differential formulation. From this delta, we go to the differential delta, or to the differential element of energy, and also to a differential formulation for the Q. And the voltage is also just given here with the as a ratio of charge per capacitance, right? So we make use of that, we insert that here. And now the question is, what is the total energy needed to charge the capacitor when we start out with the charge which is 0 and eventually go up to a charge. So the initial charge is Q prime is equivalent to 0, and then it turns into Q prime is Q. So the prime is just a different way of notation to get not confused with our integration constant. So you see, you appreciate the step how we started out. We said we take a small amount of charge that we move from conductor from one conductor to the other conductor. That requires a small amount of mechanical uh, energy to put in, because we have to drag the charge and move it over to the other conductor. At the same time, we feed also energy into the system, and we are up to figuring out how much energy is being put into the capacitor. All that what we move on charges, all that energy that we put in will be eventually stored in the capacitor in terms of electric energy. And this amount of energy that we have to put in to transfer a small amount of charge, that depends on the force of the electric field and the path that we drag the charge through. But this integral over the electric field and the path, that is just absorbed into our voltage. That the definition of our voltage is how much work, you remember how much work per charge we have to perform. That was our definition of the voltage, work per charge. So now this is our work per charge times the charge. And now we say we make this very small, so we get into a differential formulation. So this becomes dW electric. So this is a differential component of the electric energy, and that is related to the voltage and the differential element of charge that we are moving, but at the same time, we know that the charge is a function of, we know that the voltage is a function of the charge, because as we move more and more of the charges to the other conductor, the electric field starts to build up. And we know that there is a relation between voltage and charge, and that is given exactly by the formulation or definition of the capacitor. So this uh, voltage dependent, this charge dependent voltage, we can just give here as uh, Q over C, because that is right, that is a definition. C is Q over U, so the capacitance is charge over voltage, so you can write the voltage is charge over capacitance. The capacitance is a geometrical, I mean, it depends on geometry and material parameters. It will have no variation in this consideration because we're moving charges, we're not altering anything at the geometry in this process right now. That would be different if we were to consider that we have a parallel plate capacitor charged and then we pull the two plates apart, then we would have a different scenario. But here we don't do anything about the geometry parameters, so we have a constant capacitance. And now you look at this, we want to know the complete energy that we have to put in as we keep charging, putting charge from one from one conductor onto the other, and we do that by basically we have to see what kind of contribution to energy we get as we integrate for the charge from 0 to Q. So the electric energy that we have to put in is integrating from 0 to Q over the differential element here of the electric energy, and that we insert from above. We integrate from 0 to Q, Q prime over C to dq prime. And also this, when I use this q prime here, this is nothing like a derivative or such. This is just q prime. I use a different constant here to denote q, just to avoid a mix-up with our q, which is here the denotes here the limit of integration. So this q prime, this is just, I could also, yeah, I just want, the significance is just that I want to avoid confusion and don't want to have the same naming for the charge inside the integral here and on the limit. So you integrate q over c, and that gives you 1/2 q square over c. And then you insert here the boundaries. So basically you get 1/2 q prime square over c, and then you insert boundaries from 0 to q. And this is the equation 1.49. And this is now the energy that is stored in your capacitor. So recall, C is Q over U. What is the unit of capacitance? Okay, what is the energy stored then? We just had computed that. The energy in the capacitor stored is this 1/2 Q square over U, which is in another way of writing it, because you see that relation, the capacitance is Q over U, so we can also replace the Q here and write instead, we can make use of the fact that Q is C times U. So insert that for one of the Q's. So then you end up with 1/2 Q over U. That is an alternative way of expressing your energy. And you can do that once more. Then you obtain 1/2 C times U squared. So this is the energy in your capacitance. And you see this is also not, this is a general formula. This is for any capacitor. And this is your equation 1.50. So where exactly is this energy stored? That's the other question. We know that we had to perform mechanical energy, and from that we concluded that the energy that we have to put in mechanically, that is also the energy that is being stored in electric energy in the end. Now, let's look what the energy density of the electric field is. For that purpose, we have here, again, a parallel plate capacitor. And that shall be charged with a Q plus on the top plate. And we have a minus Q on the bottom plate. So plus is on the top. We have minus Q here on the bottom. We have a separation of these plates, which is given by D. We have also a plate area, which is denoted by A. And then we have an dielectric material between the plates that shall be epsilon naught times epsilon r. That is our epsilon that is in between. We have an electric field, a homogeneous electric field inside here. And if you look at the geometry, then because it has an area of A for the plate and it has a separation, we also have a given volume in between these plates. Maybe I should start to give you that. Almost forgot about that. Here's the sign-up sheet. So we have a volume between the plates, and that volume is given by the size of the plate, I mean the area of the plate and the separation of these plates. So also we have our surface charge that is given by the charge on the plate and the area that gives us our flux density. And we have computed in the previous setup how much mechanical energy we have to put in, and also concluded that this is the electrical energy which is stored in the capacitor. That electric energy is Q times U, charge times voltage, and there's a half missing, and that is the charge. We see from above here that charge is related to the flux density and the, or let's say first it is related to the surface charge and the area. So that would be our A times sigma. This is our charge, right? As we see above. And then the voltage is given by the electric field and the separation. This is our voltage on the capacitor. And this would be 1/2 times A. The sigma, on the other hand, is given also as a it's given as a electric displacement field or the electric flux density. Then we have this times the electric field times D. And now you can take the product of the area of the plate and the distance. And we said that it's actually a volume that we obtain. It's 1/2 the volume of the, basically the volume which is in between these two parallel plates of the capacitor times D times E. So if you are going by, so this is quite actually an interesting thing, because we have in the first step we were just saying that we are moving charges from conductor 1 to conductor 2. We said we have an electric field, we have to move it through, and we concluded that this total energy that it is needed to charge the capacitor, that is purely on that mechanical work that we have to perform in course of this charging process. And we also can conclude that this mechanical work that we need to charge, we have to put it in. We have somehow always a conservation of the energy, so that mechanical work that we have inserted, that we have that must be stored in some way in this capacitor, and that is basically it is stored as electric energy. And now, using this formula, you relate here the Q the um, to the flux density, and you relate the voltage to the electric field. Then you see that this electric energy has a dependence on the volume of the material that you have in between these parallel plates and the flux density and the electric field. And it shows you actually that it is also true that the energy that you put into your capacitor, in the end, it is not stored on the plates, it is stored in the field that you have in between these plates. That's where your energy has gone to. And instead of taking the energy, or in addition, alternatively, of the capacitor as such, we can also look now at an energy density. So we look at the energy density of the electric field, and that we denote now as a small W. This before was a capital W. That is obtained as the capital W L, so the work of the, or the energy of the electric field divided by the volume. And you see that immediately we have here 1/2 times volume times flux density times electric field. So we divide it by the volume. What remains is here 1/2 times electric field times electric flux density. So always keep in mind flux density, and that is you can say d field, you can say electric flux density, or the electric displacement field. That is all the same. That's different wording for the same thing. Flux density, electric displacement field, or just short d field. And in some way, maybe the flux density is also quite nice because it gives you this aspect that it is really a quantity that is taken over square meter, over an area, while the electric field is quantity over meter. Always you integrate the electric field over a path. The flux you integrate always over an area. So you have 1/2 E field times D field. That gives you the energy density of the field. But now you have, of course, this relation between the electric field and the flux density. So you can also express it here in terms of electric field squared times permittivity. Or you can also say 1/2 over permittivity times the d field squared. That's your equation 1.51. So the energy is carried by the E field and D field directly. This holds also for vacuum. So also independent of the material you have, the energy is carried by the electric and the field and the D field. So this is a very important aspect because your E field basically can carry energy. And of course, then very important takeaway then this, because you have the energy stored for the capacitor, it stores in the electric field, but when you can also get to electrodynamics, then also there you have the case that the energy is stored in the electric field and also in the magnetic field then in this scenario. And that is possible also in a vacuum or in arbitrary dielectric media. And this is basically a basis for the electromagnetic waves and also for wireless energy transmission and communication. So I want to highlight that. This is the basis for electromagnetic waves and wireless energy transmission. Energy transmission and also communication, wireless communication. So, do you have questions? No? This brings us actually to the conclusion of the first chapter. And my questions for you, do you want a 5 minutes break or shall we jump into the second chapter? Okay, let's have 5 minutes and then let's have a quick preview on the next chapter, but really tomorrow you'll enter it into it.
For you school, to when you use the work, here isn't the formula wrong? Q square over C. People over U.
Yeah. There's an error, yeah. Please correct here in the equation 150 is Q square over C. Thank you for catching it.
Professor, has the C paper been set already? The C paper for this
Almost, yeah.
1.7, 1.8.
Hmm?
So it's
Sorry, which topic?
so the topic cover for C.
Okay. I would say definitely we will not go beyond chapter 2. But we will have a little bit on chapter 2 also. But chapter 2 is it's it's a bit on currents and current density. It's not. It's yeah.
Charges.
Mm-hmm.
So why is it that the formula is miscribed? Plus Q, so E does shame E does negative E.
Because here we just this a bit because we have been a bit casual about it. We just want to have the absolute value, and so for the absolute value, the sign doesn't matter anymore. We have it. That sign would give us the direction of the force vector, but we were just interested in getting the absolute value. So in that sense, it's a bit sloppy, but it's just we just wrote down the absolute value, and the absolute value. If you put in the minus and take the absolute value, it will drop out again. So it is correct like that, but this is because.
So if it's negative, it's in the other direction.
If you put in the we know that these are of opposite charge, so we know they repel each other, and now we have to see which side we're looking at. What is all your coordination system? Then you have to think about in which way to write it. But we said, okay, we know the direction. We know already from symmetry. We are just interested at that point in the magnitude, and in the magnitude the minus will drop out. So that's why we wrote just magnitude of the force and not the full force vector by magnitude and direction. So because we said that we do by inspection the direction, we are just interested in the magnitude, and there the minus does not matter. So the minus, we can put it in, but because we would do a magnitude on the other side also, that it will fall out again. Yeah.
So can I just clarify what does the E and D field mean? Like the E means the electric field, then the D means the displacement. But what does that mean? What's the difference? Yeah. How does it differ?
So the electric field you obtain from the force field, right? You have Coulomb's law. You take the force field, and you have a force acting. If you have one charge, you put in another charge. They always exert a force mutual on each other. So you basically for the electric field, you take out you see force per charge. So this electric field is directly related to your force vector. If you look at the displacement field, then that is actually a flux density. It is also the reason why we introduced it. We wanted to have something which is a field quantity which is, so to say, neutral of the material properties, and which is only the charges, the sources involved are relevant. Because we had the situation that for the Coulomb law, you have here this proportionality 1 over epsilon, yeah, and this epsilon, there your material properties enter. And these we wanted to have removed in that other field. The advantage is with this displacement field or the flux density, we can do these surfaces. We can do a control surface. We can have some charge here, and we can integrate over this flux, and it tells us about the charges. The type of material that is involved here is not of any relevance. So this is kind of a different concept a bit of the electric field. But then at the same time, you have the flux density is also related very closely. So there's a very close interaction, but conceptually it is also something different, because this is a flux. This is something that penetrates through some area, and this is more like a force vector. So they go hand in hand, and yet they are different also from conceptually. If you are, I mean, you know that you can often you may have a D field and you rewrite that and as a permittivity times electric field. But if you do such an integration, then you will of one of these quantities, you see the type of integration that when you use them is very different. The electric field give you something. If you integrate over the electric field, always over a curve usually, to get the work, to get the voltage. And for the D field, you like to do these surface integrals to give you some insight over the charge. But at the same time, you can express, as we did here with the electric density, you can also transition, and you can the electric you can write as a product of E and D or just of the E field, but then you have to, yeah, so it's not very sharply separated in sense, but it's uh, it is a different concept. One tells you maybe something more about the forces, and the other one about the sources, about the charges that are involved in there. So, and they're going hand to hand, but it's um, hmm? It's a bit tricky, yeah. It's and need to appreciate that the difference between, but keep always in mind that D field is a flux. There's something that is flowing, basically. It tells you something about the sources. In the electric field, no, this is something that gives you something about a force. So the one is more oriented toward the sources, the D field, and the E field is more what these sources are causing, the force field, so to say. But they are interrelated with each other.
KYKX in there.
Hmm?
What does KY?
Oh, this was just a question to the previous problem. Uh,
Oh, they use KY.
This was, I think we had this potential problem where the X component was an electric field. We had an electric field where the X component was Ky and the Y component were Kx. And there was a question when we integrated why one component was vanishing, and it was because we're taking the inner product. Yeah.
Thank you.
Okay, let's get a bit started as a preview for what we're going to start tomorrow. By the way, because there keep coming questions for the continuous assessment, certainly we're not going beyond chapter 2 on the continuous assessment, because the question how far do we go? So chapter 2 is also fairly short, but if we might, I think, yeah, certainly we will finish it before before the before Friday, but we will not enter. This will be chapter 3. Then definitely will not be relevant for the continuous assessment. And chapter 2 is also a fairly short chapter. Then chapter 3 is a bit slightly long, and chapter 4 will be also very short. And well, let's get a bit started. This far, we had been always on the situation where we are in the static scenario. And now we want to see what happened when we have stationary currents. And we want to know what is an electric current and what is a current density. So up to now, we had carrier distributions, but we always considered the stationary equilibrium case. I mean, also for the capacitors, the charges were always already placed. Only now in the last section, we were interested in what happens if we move them, but we also there were not really in the dynamic process interested, but we wanted to know what happens as we move charges from one conductor to the next conductor, how much energy do we put in the field, but always we had here a carrier distribution given, and we were in a stationary and equilibrium situation and in rest. So means all the forces were in equilibrium, so you have always a force balance. And what we are changing now is that we're looking at charges which are moving. So they have a given velocity, and that is what you see here indicated, is that you have a number of charges and they exhibit now a motion, and that is specified with a certain direction given by the vector and a magnitude of the vector. So you have a velocity field here that is attributed, and you see they can have different velocities in the sense that by magnitude here you have a fast moving carrier and a slow moving here, and they're also slightly different with their directions. And where is this relevant? Well, that is relevant, of course, in a lot of cases. We have electrically conducting materials, and as soon as we don't want to look at an equilibrium state, then it becomes relevant. Actually, even in the, yeah. So if you have a conducting material, you have about 10 to the 15 to 10 to the 22 mobile carriers per cubic centimeters. And that is relevant in applications where you're looking at gas discharging processes, or if you look at plasmas, if you have a plasma light or a lamp, for example. Then if you have electron beams, you have moving um, charge carriers. So you have here the picture of a plasma lamp where you have basically an oscillating electric field that is exciting your carriers, and then these carriers move and they also collide with each other, and this collision causes some that when you have these atoms in this gas that are being moved at high speed, and if they collide, then they may pick up some of this energy and elevate electrons to higher orbits. And when they fall back, then there can be emission of light. So if you compare that, we had earlier made this comparison of that river where we have particles which are flowing with also within a velocity field where each particle has a given magnitude and direction for its velocity. And the carriers, they also move similar in the sense because they also have a velocity vector attributed to it. What is the driving forces? That is then the electric force, so the electric field, basically, so to say. And the electric field that we have seen can be obtained from the scalar electric potential, that phi. So that is minus the gradient of phi, that is the electric field, that is a driving force for your electric carriers. But this is not the only driving force. Also, you can have the particle density itself being a driving force, because if you have carriers and they are not homogeneously distributed, then they will also start to flow based on that. Basically, n here is your carrier density. This is the number of carriers per volume element. And if you have that not even, then the gradient of this number of carrier, so in the number of carrier densities, will cause them the carriers to redistribute, which also makes sense because if you have them very closely together in some region and then they get more sparsely in that region where they're closely together, they will obviously exert more electric force within each other, so mutually exert force on it, and they will try to separate further. So they're trying to move from where there are a lot of charge carriers to regions where there are less charge carriers. So this is just given by the gradient. So the gradient would be also the gradient of particle density is also a driving force, and that is basically some diffusion current. But also temperature gradient, if you have temperature, that is always usually the case, that you're not operating at temperatures close to zero, then this temperature also gives energy to your atoms and to your carriers, and that will cause some motion. What does stationary means as compared or opposed to static? That means that your physical quantity does not depend on time. So independent of you have a scalar or a field quantity, it has no variation on time, and that means locally it is locally constant, at least. Examples are the electric charge. So if you are in the static scenario, then that is what we had seen this far. All your charges are located at a fixed position and they are in rest. And there is an equilibrium of forces. This is what we have seen when we had the Coulomb law. We were never, okay, we not necessarily had here force balances, but we were always then assuming that our charges are being pinned to their location, and we did not account for any motion of charges. And now, on the other hand, if you are in the stationary scenario, then your charges can move. So they can move based on a certain velocity. That velocity can also be, in general, position dependent. However, this particle flow is then constant and not depending on time. So you have to appreciate, I mean, because your charge is moving, it is changing its position in time, but that velocity vector that describes this assembly of charges, that has no temporal variation. that is as a velocity field then can vary locally, but it does not vary temporally. What is the electric current? So you have here more global and a local perspective. So you have the number of charge carriers, and now you need some kind of volume for reference. And these charge carriers, they will pass through this area, and they will do that within a time interval. So this number of the change of carriers, that number of carriers that pass through this interval per time unit, that gives you your current. So this is a change of charge per time. Your charge is in ampere times second, and ampere times seconds per time gives you ampere. So that means the current, the unit is the unit of current is ampere. So also note, this here is not a closed surface. This is just not like what we had in Gauss law, where we had an enclosing and closed surface, but this is an arbitrary area that you pick, and within this area, a certain amount of charges are passing through per time. So charge per time, that gives you the current. You see the current is dependent on the area, and hence this whole thing is a kind of an integral quantity, because you have to integrate over the entire surface all the charges that are passing through. You also want to introduce, addition to this integral quantity, a local quantity, and that is the so-called current